Hey guys, this is Rattan Kumar, 21BC1133, and today we're going to be looking at part 3 of the NAND2TETRIS project. So first we're going to be looking at the 1-bit register. So that's simple, as the name suggests. It holds 1 bit of data, right? So you can use that for like any process. Maybe you want to hold 1 bit of data. It can be like do I say a flag or a counter or something like that. So in this, it's simple. You have an input, output, and load. So input is the input that you give, and load is the like a flag which tells you what to do with the data, either like output the data or like increment the data or something like that. So we'll see the code of the 1-bit register. This is the 1-bit register code. Simple. It's a mux, and it's just one input, one load, one output, right? And then the mux is to choose the input, to tell you what to do with the input is why we have the mux, right? So let's execute the code, load the chip, then let's load the test script, and let's execute it. So if you see the input, right, you can see a single bit input and a single like load bit, which will determine what you do with the input bit. So let's we have the output. See the output. This is the output, right? We have ones and zeros depending on. So you have the input zeros, ones, zeros, ones, and you have the load bit, which will determine what the output will be, right? And let's compare it with the compare file. It's the same. So none of the values have changed, right? So our output is right. So let's move on to the next one. So it's the 16-bit register. So it's similar to the 1-bit register. It's just a combination of 16 1-bit registers. So it can hold 16 bits of data. Same thing, you can use it for any process, 16-bit data. So you have an input of 16-bit, output of 16-bit, and a load bit. Okay, we see the code here. See, it's just a combination of 16 1-bit registers. That's it. So let's run this code. Have this, let's load the chip. 16-bit. Let's load the test script and let's execute it. So that's done. So as you see here, right? So you see the input. The input is of 16-bit, right? So before in the 1-bit register we saw 1-bit input, but here we have a 16-bit input, but the load will be the same 1-bit load. The output will be a 16-bit output. Let's see the output. Here we have the output, right? And let's compare it with the compare file. It's the same. None of the values have changed. So our code works. Let's move on to the next one. So here we have RAM. So RAM, basically 8 RAM or RAM 8. What it does is basically it's a culmination or a combination of 8 16-bit registers. So in this you feed the 16-bit input to all the registers, all the 8 16-bit registers which are present here, and then you'll use mux demux to select which register to use for the given process. So load will help the mux and demux to determine which RAM to use for the given process, and the output will also be a 16-bit output, right? So let's see the code. Here in this code in RAM 8, as you can see, there are 8 registers, 8 16-bit registers, right? And then you have the mux and demux to determine which register to use for the given process, right? And then you have the 16-bit input and the 16-bit output. Let's run this code, load the chip, RAM 8, and then let's load the test script, RAM 8. Let's execute it. So that's done. As you can see, you have a 16-bit input and then a 1-bit load and the address 7. This address 7 helps to choose which register to use for the given process. So that determines how the output determines or changes the output. So let's see the output. We've got the output. This is the output, right? And let's compare it with the compare file. None of the values have changed. So our chip works. It's right. Let's move on to the next type. So this is the basic RAM. This is the most basic RAM that we will implement. We have other types of RAM like RAM 64, RAM 512, and all those things in 16K. So what it is basically, in RAM 8 you have 8 16-bit registers. Similarly, in RAM 64 you will have 64 16-bit registers, but each 8 16-bit registers form a RAM 8. So 8 RAM 8s will form a RAM 64, and 8 RAM 64s will form a RAM 512, and so on. So it goes on till RAM 16K. That's what we're going to execute. So let's see the code of RAM 64. As I said, so here we have RAM 8, right? In RAM 8, we had 8 16-bit registers. And then here in RAM 64, we'll have 64 16-bit registers. But instead of writing it like that, we're writing it as 8 RAM 8, right? And then it's the same mux and demux to determine which RAM to use for the given process. And then this will be a 16-bit input, 16-bit output, same load and address, right? And then you have the mux demux. So let's execute it. Let's load the chip, RAM 64, then the test script, RAM 64, execute it. This will take quite some time, so that's why I've increased the speed to fast, right? Okay, so our output is done. You can see here, right? You have the load single bit and the address and the output, right? So let's check it, check the output. We have the output here, right? For different address values and different inputs, we have different outputs. Okay, and let's compare it to the compare file. See, none of the values have changed, right? So our chip works, implementation works. Let's move on to the next type of RAM, which is RAM 512. Again, we are moving up the ladder. So 8 into 8 is 64, 64 into 8 is 512. So again, 512, RAM 512 will have 512 16-bit registers. Again, we'll use mux demux to choose which register to use. But here, instead of writing 512, that's a tedious process. So we'll have 8 64 RAMs, right? Then we'll use the same mux demux to choose which RAM to use for the given process. So let's execute it, load the chip, RAM 512, and then the test script, RAM 512 run. Let's execute it. It has executed, right? So let's look at the output. This is our output. Again, this is difficult to understand, but we have these address values, inputs, and the corresponding outputs. So the address value and the load value determine the output. So let's compare it with the compare file. See, none of the values have changed. So our output works, right? I mean, our chip works. That's good. So now we're moving up the ladder from 64, we went to 512, and now we're at 4K. So this has 4K 16-bit registers. But instead of writing that, we've written it as 8 512 RAM 512s, right? 8 RAM 512s. And then we have the same mux demux to determine which RAM to use, and this will in turn affect the output, right? And we have the same 16-bit input, 16-bit output, and the load bit. So let's execute this. Go to this, load the chip, RAM 4K, test script, and is executed. Okay, so it is executed. So let's look at the output. This is the output, right? And let's compare it with the compare file. So yeah, none of the values have changed, right? So it's the same. So our code works, our chip works. So let's move on to the next type. Okay, from 4K we're gone to 16K now, right? So again, this has 16 K or 16,000 16 registers. But instead of mentioning it that way, instead of what do I say, writing it that way, you can write the code 16,000 times as well. But instead of doing that, we are writing it as 4 RAM 4K. So it has 4 RAM 4K, and then you have the same mux demux to determine which RAM to use for the given process. That'll affect the output. Uh, so we have a 16-bit input and 16-bit output, same load bit and everything. So let's see the implementation. We have the 16K chip, load the test script 16K, and then let's run this. So let's go to the output. This is the output, right? So let's compare it to the compare file, and none of the values have changed, as you can see. So our chip works, implementation is right. Let's move on to the last one of the day, right? So this is a program counter. So a program counter is basically a counter, right? So a counter what you use to during the execution of any program, use it in the system. So what it has is it has a 16-bit input, a 16-bit output, and three flags or three bits which determine what we have to do with the input, right? So as a counter means it counts, maybe counts the number of times it is executed or something like that. So for a counter, you need to be able to like increase the counter, set it to a certain value, or like reset it after a certain process. So here we have load. So load determines what we do with the counter. So either set it to a certain value or something like that. INC is incrementing. So you increment the value. So a counter means you should be able to increment it by one, right? That's what a counter does, right? Or increment it by a certain value. So increment helps it increase the value, and reset. Reset means it'll set back to zero after a certain process or something like that. So these are the three bits that are present in the program counter. So let's look at the code of the program counter. So this is the program counter. Here you have a 16-bit input, 16-bit output, and then the three single-bit flags, or you can say something which controls what we do with the input. So here we have increment 16. We have seen these before in the previous part of NAND2TETRIS, and that we see increment 16 increments the 16-bit input by one. Okay, mux, demux, the three muxes, you use this to determine what you do with the input using the three uh, flag bits, and then the register. This register is used to store this data. That's it. So let's look at the implementation. Let's load the chip. Uh, PC program chip, program counter. So we have loaded the chip. We have the HTTP code here, and we have the test script. Let's run this. Yes, so the execution is done. Let's see the output. So this is the output. You have the time, you have the input, the reset, load, the three flag bits, and the output. Let's compare it with the compare file. Yes, it's the same. So our code works, implementation works. So that's it for this part of the video.